Let's take a look at this example. I will start solving this problem from finding Z total. Why? Because I have given resistance and I have given power factor. Formula for power factor says power factor is equal R over Z total. I can solve Z total from this formula. So if you are going to use algebra, you'll find that Z total is equal R over power factor, where this is equal resistance 1.5 kilo ohms divided by 0.375. This is equal 4 kilo ohms. Please notice that my total impedance is incomplete. I'm supposed to find also the angle. In order to find the angle, I'm going to use the, again, formula for power factor, which says that power factor is equal cosine of angle theta. If you are going to solve this formula for angle theta, you're supposed to obtain angle theta is equal inverse cosine of given power factor. So I have 0.375. Please notice that next to the value of power factor we have word lead. It means that in this circuit current is going to lead the voltage source by certain angle which we are going to find, right? And it means that our angle is going to be negative. So this is equal negative 67.97 degrees. Okay, so this is the angle which I'm going to write next to Z total. Again, this negative sign is telling me that I have to write word lead next to the power factor, and at the same moment it means that the current in the circuit is going to lead the voltage source by angle 67.97 degrees. So I have Z total equals 4 kilo ohms and angle of negative 67.97 degrees. This is my Z total. Why I have to find Z total? Because in order to find current, I basically would like to solve Z total first, and after that, if I have voltage source given, I can find very easy I total. I total in this case, right? Don't forget that this is series circuit. I total is also equal IC. That's why I have to find I total, and this is also equal IL, and this is also equal IR. Okay, so if you want to find I total, simply use Ohm's law and say that voltage source divided by Z total is going to give me the current in my circuit. Don't forget that this is the voltage expressed in the terms of sinusoidal equation, so it means that we are talking about the peak voltage. So the current which we are going to find is also peak. So voltage source is equal 30 volts, and Z total we calculate is 4 kilo ohms and angle of negative 67.97 degrees. This is equal 7.5 milliamps and angle of 67.97 degrees. So this is the value of the current in my circuit. Please notice that the current has the positive angle, so it means that the current in the circuit is going to lead the voltage by angle of 67.97 degrees. So, as we said before, I total is equal to IC is equal to IL, and this is also equal to IR, and this is equal 7.5 milliamps and angle of 67.97 degrees. Next, we're supposed to find voltage across the resistor, voltage across the inductor, and voltage across the capacitor. Someone is going to say, okay, this is very easy, but I'm going to complicate your life a little bit because I'm going to ask you to find these voltages by using voltage division law. Someone is going to ask why? Because we need to practice. Students have big problems with voltage division law. That's why I'm going to solve those voltages by that law. That's why I'm going to write that. VR is equal voltage source resistance over Z total, where voltage source is equal 30 volts and I have resistance is equal 1.5 kilohms over Z total, and we found Z total is equal 4 kilohms and angle of negative 67.97 degrees. This is equal 11.25 volts and angle of 67.97 degrees. Okay, so this is the voltage across the resistor. Next, we're supposed to find the voltage across the inductor. In order to find voltage across the inductor, we're supposed to find X of L, or impedance of the inductor. But in order to find the impedance of the inductor, I would first find the impedance of the capacitor, because capacitance is given. Okay, so in order to do so, I'm supposed to write the formula X of C is equal 1 over J omega C. So this is equal 1 divided by J, and omega is 1 times 10 to the 6th radians per second times C, which is equal 220 picofarads. This is equal 4.54 kiloohms and angle of negative 90 degrees. So this is the capacitive reactance in my circuit. If you have capacitive reactance, you can find also the inductive reactance. I'm going to use the formula Z total equals resistance plus X of L plus X of C. I'm going to use this formula because my Z total goes with angle. If I have angle, I can use this formula. So in order to find X of L, I'm going to solve this formula for X of L. X of L is equal Z total minus R and minus X of C. So this is equal, Z total we found is 4 kiloohms and angle of negative 67.97 degrees minus resistance, which is equal 1.5 kiloohms, and minus X of C, which is equal 4.54 kiloohms and angle of negative 90 degrees. This is equal X of L 832.05 ohms and angle of 90 degrees. So we found the inductive reactance. Now we are ready to calculate the voltage across the inductor. So we have VL is equal voltage source times X of L over Z total, where voltage source is equal 30 volts times X of L 832.05 ohms and angle of 90 degrees over Z total, which is equal 4 kilo ohms and angle of negative 67.97 degrees. This is equal 6.24 volts and angle of 157.97 degrees. Okay, so this is the voltage across the inductor. Next, we're supposed to find the voltage across the capacitor. So VC is equal voltage source times X of C over Z total. This is equal 30 volts times X of C 4.54 kilo ohms and angle of negative 90 degrees over Z total, which is equal 4 kilo ohms and angle of negative 67.97 degrees. This is equal 34.05 volts and angle of negative 22.03 degrees. Okay, we found voltage drop across each component. Now we're supposed to verify if our answers are correct. In order to verify my answers, I'm going to use KVL. Remember that the sum of the voltage drops across each component is going to give me the voltage source. So I'm going to have voltage source is equal voltage across the resistor plus voltage across the inductor plus voltage across the capacitor, where voltage across the resistor we found is equal 11.25 volts and angle of 67.97 degrees plus VL, which is equal 6.24 volts and angle of 157.97 degrees plus VC, which is equal 34.05 volts and angle of negative 22.03 degrees. Voltage source in this case is equal 29.99 volts and angle of negative 0.005 degrees. So we can say that this is approximately equal 30 volts and angle of 0 degrees. So it means that our calculations up to this moment are okay. Next, we're supposed to find the true power in the series circuit. Okay, because we are dealing with the peak current, because we found that current by using peak voltage, I'm going to write power. True power is equal to 1/2. Because I'm using peak values, I'm supposed to write 1/2 times IR squared times resistance. So I have 1/2 7.5 milliamps raised to the second power times the resistance. Resistance is equal 1.5 kilo ohms. This is equal 42.18 milliwatts. Okay, so this is the true power in my series circuit. Next, we're supposed to find the reactive power. In order to find the reactive power, I'm going to find first the total reactance. Okay, so total reactive is equal X of L plus X of C, where X of L we found is equal 832.05 ohms and angle of 90 degrees, plus X of C, which is equal 4.54 kiloohms and angle of negative 90 degrees. This is equal 3.7 kiloohms and angle of negative 90 degrees. So this is the total reactance in my series circuit. So now I'm ready to find the total reactive power. So Q is equal 1/2 I total raised to the second power times XT. So I have 1/2 I total equals 7.5 milliamps raised to the second power times X total, so I have 3.7 kiloohms, gives me 104.06 millivolt ampere reactive. Okay, so this is the total reactive power in my circuit. Now we can find the apparent power. So I have S equals 1/2 I total raised to the second power times Z total, which is equal 1/2 I total 7.5 milliamps raised to the second power times Z total 4 kiloohms. This is equal 112.5 millivolt amp. Okay, so this is the apparent power in my series circuit. Now we're supposed to find the parallel equivalent circuit. In order to do so, we're supposed to find the total admittance. Y total is equal 1/Z total. At this moment, I would like to ask you to switch your calculators to rectangular mode in order to get the answer from this calculation in rectangular form. So I have 1/Z total, which is equal 4 kiloohms, and angle of negative 67.97 degrees. The answer is 93.77 microsiemens plus J 231.74 microsiemens, where the real part of my answer is my conductance and the imaginary part is my capacitive susceptance. So now I'm ready to find the powers. The true power, P true, in my parallel circuit is equal 1/2, and I have voltage source raised to the second power over the resistance in the parallel circuit. Okay, let me just remind you that right now we try to find the values of components, right, in the parallel equivalent circuit. So this is RP and this is CP, and this is my voltage source. Now, but please notice that we didn't find the resistance. Okay, someone is going to say, oh, but we didn't find the resistance. We're supposed to find the resistance. Actually, we don't have to find it. If you want to, you can, but you don't have to. You have to just keep in mind that we're supposed to copy down 1/2 and rewrite this fraction as the product of two fractions, voltage source raised to the second power over 1 times 1 over Rp, where 1 over Rp is nothing else, just the conductance. Okay, so I can rewrite this expression as 1/2 voltage source raised to the second power times G. Okay, so this is equal 1/2 voltage source is equal 30 volts raised to the second power times conductance 93.77 microsiemens. So true power in my parallel equivalent circuit is equal 42.19 milliwatts. If you are going to compare with the true power which we obtained in the series circuit, right, it was equal 42.18 milliwatts. So as you can see, these two values are very close to each other. Okay, so we can say that our calculations up to this moment are okay. Now the problem is asking us to find the reactive power in the parallel equivalent circuit. So I'm going to write QP is equal, means the reactive power in the parallel circuit. This can also be called QC, because this is the reactive power at the capacitor, is equal 1/2, and I'm going to use exactly the same format which I used over here, voltage source square times, in this case, BC. So this is equal 1/2, and voltage source is equal 30 volts raised to the second power times BC, 231.74 microsiemens. This is equal 104.28 millivolt ampere reactive. Okay, so this is the reactive power in the parallel equivalent circuit. Let's compare what we have got in the series circuit. In the series circuit, we got 104.06 millivolt ampere reactive. Okay, we can say that these answers are also very close, even if this is 0.6 and this one is 0.28, so we can say that this is also good. Now we can find the capacitance in the parallel equivalent circuit. In order to do so, I'm going to use the formula for the capacitive reactance. So I have X of C in my parallel circuit is equal 1 over omega C in my parallel circuit. But again, someone is going to say, but we do not have the capacitive reactance. We didn't find this. So what I'm going to do, I'm supposed to just, instead of XCP, write simply that this is nothing else, just 1 over BC. Okay? Because X of C is equal 1 over the capacitive susceptance. So this is equal 1 over omega Cp. If you are going to use algebra, of course you're supposed to cross multiply. you are going to find out that Cp is equal Bc over omega, where Bc is equal 231.74 microsiemens over omega 1 times 10 to the 6th radians per second. This is equal 231.74 picofarads. So at this moment we can say that the problem is solved.